Hello everyone, welcome back. So in this lecture we are going to discuss about the equivalent stiffness of system in which beams and springs are connected together. So to understand that system, first of all we'll discuss about the parallel system, right? So here we consider the parallel system. So in this we are considering two systems. In this we are considering two springs are connected in this way, right? This is K1 and this is K2, and length of these springs are L. Now if we apply the force at this place F, then this will get stressed by X. This is X, right? So now if we draw the free body diagram of this system, then that free body diagram will be something like this. And this will experience a force F1 and this will experience a force F2, and there would be a force F1 and this is force F2. Here's force F1 is equal to K1x and F2 is equal to K2x, and this is external force F, right? So this system can be represented as there is a system of K equivalent stiffness and the length of this spring system is L plus X, right? And there is a force F, right? So now if we apply the force equilibrium approach at this system, then we can write F is equal to F1 plus F2, and from here we can write F equals to K equivalent multiplied by X. So this can be written as F1 is K1x and F2 is K2x. This is F, right? So from here we can write X multiplied by K1 plus K2, and here F equals to K equivalent multiplied by X. So we can compare these two equations. So we can write K equivalent multiplied by X is equal to K1 plus K2. So multiplied by X. So this will be K equivalent is equal to K1 plus K2, right? So this is equivalent stiffness of this system when springs are connected in parallel. And if we observe that the forces in both of the springs are different, so we can write forces in both of the springs are different. And second thing, we can observe that the displacement of both of the springs are same. Displacement of both of the springs are same. So we can make a statement that if springs are connected in such a way that under the action of force, their displacements are same and their forces are different, then springs are in parallel, right? Now we'll consider the series system. So second, we'll talk about the series system. So to discuss about this, let's consider two springs are connected in this way. This is spring 1 and this is spring 2. So K1 and K2 are their stiffness and their lengths are, this is L1 and free length of this is L2. Now we apply a force F here. Okay, and because of this force there is a displacement X, right? So now we can draw this system, or we can represent this system something like this. This is the spring 1 and the displacement of this spring is x1, right? So total length of this spring is L1 plus x1, right? Now this is the spring 2 and length of this spring now becomes L2 plus x2, right? And there is a force F. Okay, so the force F1 in this spring is equal to K1 x1. So from here we can write x1 is equal to F1 over K1, but from here we can say F1 is equal to F only. So this is F over K1, and from here we can write F equals to K2 x2, and from here we can write x2 is equal to F over K2, right? So now this system can be represented by a equivalent system. There is a spring of K equivalent stiffness and this is complete L plus X, right? And this is force F. So I write the equilibrium equation over this, then this would be F equals to K equivalent multiplied by X. And from here we can write F equals to F1 equals to F2, and we can write total displacement X is equal to X1 plus X2, right? So X1 is equal to F over K1 and X2 is equal to F over K2, right? So this can be written as F1 over K1 plus 1 over K2, and this we can write as F K1 plus K2 over K1 K2. And now if we compare these two, from here X equals to F over K equivalent. So now if we compare these two, then we can write F over K equivalent is equal to F multiplied by K1 plus K2 divided by K1 K2. So from here we can say 1 over K equivalent is equal to K1 plus K2 over K1 K2, and K equivalent of this system is K1 K2 over K1 plus K2. So this is how we can find out the equivalent stiffness of the series system. So now we can observe that the forces in both of the springs are same. Forces in both the springs are same, and displacement of both the springs are different, right? So we can make a statement: if the springs are connected in such a way, when the forces in both of the springs are same and displacement of both of the springs are different, then we can say springs are connected in series system, right? So now we'll consider a cantilever beam connected to a spring in such a way that cantilever beam with spring. So third, now we'll consider a cantilever beam with spring. So let's consider this is a cantilever beam, and this cantilever beam is connected to a spring in such a way, and the length of this spring is L1, right? And stiffness is K, and here Young's modulus of this beam material is E, and area moment of inertia is I. So now if we apply a force F at this place, this beam will deflected like this, right? And this will be delta, right? So as we know that this delta is equal to F L cube over 3EI, right? And now we can draw the free body diagram of this system. So free body diagram will be something like this. This is the cantilever beam, right? And this will experience a force F here, and this is the spring. So in the spring there would be a force, let's say this is Fs, and there would be a force Fs in this direction, right? So now we can say the force in the spring is equal to force in the spring is equal to Fs, and force on the cantilever beam is equal to F minus Fs, because this force is F and this is force Fs. So this is F minus Fs, and displacement of both the systems are equal to delta, right? So we can say force on both of the systems or both of the forces in both the components of system, means we are talking about beam and spring. These are two components of this system are different, and displacements are same for both of the components. So we can say this would be the parallel system, right? So here we can, as we know that the equivalent stiffness of cantilever beam is 3EI over L cube, and the stiffness of the spring is K. So we can say K equivalent is 3EI over L cube plus K, right? Because both of the systems are in parallel, spring and cantilever both are in parallel. So this is, we can write beam and spring are in parallel, because we know that the parallel system have the four different forces and same displacement. Now let's consider another example of simply supported beam. This is the simply supported beam with spring. So here we can consider this is simply supported beam, and there is a spring which is connected at mid span of this beam, right? And length of this spring is L1, and stiffness is K, and this is E and I, Young's modulus and area moment of inertia of this beam. This is midpoint L by 2 and L by 2. Right? So now if we apply the F force at the midspan of this beam. So if we apply the F force at this place, right? So this beam will be deflected like this, right? So this is the displacement of this beam, and same displacement will be created in the spring, right? So this delta is given by this delta of the simply supported beam at the mid plane span is given by FL cube over 48 EI, right? So now if we draw the free body diagram of this system, then FBD of this system would be like this. This is the spring and there would be a force Fs, and similarly this is the beam, and this beam will be experience a force Fs in this direction, and this is external force F, right? So we can say the force in the spring is equal to Fs, and force on the beam is equal to F minus Fs, right? So from here we can say force in both of the component of the system, forces in both of the components of the systems, that means beam and spring. These are two components of the systems are different. So forces in both of the components of the systems are different, and displacement are same. So displacement of the spring is also delta, and displacement of this beam is also delta. So this is the property of the parallel system. So we can say beam and springs are in parallel. So as we know that the equivalent stiffness of the beam KB can be written as 48 EI over L cube. Formula for this we had derived in the last lecture, so you can watch that to get this formula. And stiffness of the spring is K. So we can write the K equivalent of this system is KB plus K of spring. So this is 48 EI over L cube plus K. So this is K equivalent of this system. So from here we can identify the combination of beam and spring as parallel or series. That depends on the combination of or how the spring is connected to the beam. So this is how we can find out the equivalent stiffness of the beam and spring combinations. So thank you.